Hello, Mrs. H here. We're going to get really stuck into some more difficult application questions while going over some common exam techniques. Water moves by osmosis in living organisms. A group of students used the following method to investigate osmosis in plant cells. When you get a method, I want you to scan through and look for what we call limitations of a method. Now, a limitation of the method is some part of that method that is not explained very clearly. What I mean is, two different people could actually interpret it slightly differently, and therefore those results wouldn't be reproducible, for example. Or you might do it slightly different each time you do it, so your results wouldn't be repeatable. So any area where it's not clear, so let's just go through and have a look. Cut pieces of plant material of equal surface area, ensuring no skin is present. Well, no skin is present, that's very clear. Okay, so we won't leave any skin on. But equal surface area, how big shall we make it? That's a limitation with the method. Rinse to remove cell debris. How long do we rinse it for? Well, I could rinse it differently to my friend. Gently pat the plant pieces dry with a paper towel. What exactly does that mean? How long should I do that for? Weigh each piece and record the mass. Yeah, that's okay. Put the plant piece in 200 centimetre cubed beaker. Cover the plant piece with 50 centimetres cubed of sucrose solution. Use the sucrose solutions of 0, 0.1, 0.3, 0.5, 0.7 moles per decimetre cubed and leave for 24 hours. Remove the piece of plant material. All of those points are very clear. If you don't follow those, then any errors will be due to silly mistakes rather than limitations of the method. Dry carefully using a paper towel. So that clearly is a limitation of the method, because we just don't know if I might dry it twice and the person in another group might decide they've got a method of drying it 20 times, rolling it in a towel or something. So that is a limitation. We could all do that differently to each other. Weigh the plant piece and record the mass. Calculate the percentage change in mass for each piece and repeat twice for each sucrose concentration. The students investigated material from 3 different plants: carrot, courgette and potato. The results are shown in the table below. We'll have a look at that in a minute. Explain why it was necessary to calculate percentage change in mass. Well, there are different starting masses, so percentage change in mass will allow comparison between plant pieces of different masses. The students identified replicate 3 of the potatoes in 0.7 moles per decimetre cubed sucrose as anomalous. Suggest a practical error by the students that might have caused this result to be anomalous and explain the likely effect of this error. Let's just have a look at replicate 3 of potato 0.7 moles per decimetre cubed. So it's at the top here, and we have a minus 5.1%, so a decrease in mass of minus 5.1% in replicate 3. But 1 and 2, 6.1, 5.9, so they're quite close to each other. 5.1 is further away. If there is less of a percentage decrease in mass than replicates 1 and 2, this must have had a greater mass when it was being weighed. So then that clue from the table, you take that and then you go to your method and think, why would that third potato chip weigh more than the other 2? Look at the limitations in the method. The one that fits the best is dry carefully using a paper towel. Now, what if on the third replicate, because of that limitation in the method, the student didn't dry it carefully enough, so it's inadequate drying, meaning that the chip would be heavier. So the answer is inadequate drying of the potato for replicate 3 meant that it was heavier, more mass than the other pieces or replicates. Use table 16 to identify which plant cells contained the highest concentration of sucrose and justify your conclusion. So we really need to have a look at the data in the table for this. Plant cells with the highest concentration of sucrose solution, if they're placed in pure water, so a solution with the highest water potential, you'd expect them to gain the most mass because of how steep that water potential gradient is. Carrot at 0%, so the highest water potential, pure water, increases by 5.87%, courgette by 7.7%, and potato by 5.77%. So courgette gains the most mass in pure water. Well, also the plant tissue that has the highest concentration of sucrose solution inside its plant cells is going to lose the least mass at the higher sucrose concentrations. Carrot in 0.7, so that's our highest sucrose concentration, decreases in mass by 6.23%, courgette by 4.27%, and potato by 5.70%. So actually courgette, that decreases by the least percentage in the higher concentrations. And the other clue that you could use is if you have a look and you remember that when you plot this in a graph, you get a line of best fit, and where it crosses the x-axis, there's no change in mass. And a no change in mass tells you the concentration inside your cell. But we don't have a graph, so we need to look at the table. Have a look at carrot. This is what I mean. Between 0.3 and 0.5 sucrose concentration, moles per decimeter cubed, you can see that somewhere between 0.3 and 0.5 there will be a no change in mass. So the concentration of the carrot is somewhere between those values. The courgette, look, we've got an increase in mass of 1.90 at 0.3 moles per decimeter cubed. And we've got a decrease of 1.23 at 0.5. The concentration inside the courgette cells is between 0.3 and 0.5 as well. But the potato actually must have a lower concentration inside of it because the concentration of the potato is somewhere between 0.1 and 0.3. So the justify your conclusion is all the data that we're going to pick off the table to write down. So courgette, because it has the highest percentage mass gain at 0 moles per decimeter cubed sucrose solution. It also has the least or the lowest percentage mass loss at 0.7 moles per decimeter cubed. And the concentration of sucrose inside the courgette falls between 0.3 and 0.5 moles per decimeter cubed. A group of students investigated the effect of temperature on the membranes of beetroot cells. A colorimeter was used to measure the concentration of the purple betalain pigment that leaked out of the cells when they were exposed to different temperatures. So we've got our temperatures up to 60 degrees C. There were 10 readings. We've got absorbency, and we've got our standard deviation already calculated for us. Using the student's t-test formula below, calculate the value of t between the data for 50 and 60 degrees C. So just have a look at what we've got here. That is at 50, it's 0.21, which is our mean, our first mean that we're going to put into the equation. And then we put our second mean in, which is 0.44. And then we've got to divide that by the square root of the standard deviation squared for A. That is 0.06. Don't forget to square it. Lots of students do that and they lose marks in exams. That's over N, which is 10, your number of readings. And then we add that to the standard deviation squared for 60 degrees C, which is 0.18 squared divided by 10. And if you follow that calculation through, you will end up with 3.83. The critical value for T at the significance level of 5% with 18 degrees of freedom is 2.10. Use the value of T that you calculated in part I to explain whether the null hypothesis should be accepted or rejected. Now, I can't see any null hypothesis that has been made, but we can make one from the information we've given. So a suitable null hypothesis would be something like, there is no significant difference between the mean absorbance at 50 degrees C and 60 degrees C. The student's t-value of 3.83 is greater than the critical value of 2.10, so we reject the null hypothesis. There is a significant difference between the mean absorbance at 50 degrees C and 60 degrees C. You need to make sure you definitely put the word significant in there, marks going for that. And you can remember this little double arrow thingy where you can put the critical value in the middle, and if your calculated statistical value is greater than the critical value, you always reject the null hypothesis. If it's below the critical value, then you always accept the null hypothesis or fail to reject the null hypothesis. The students plotted the data onto a graph shown in figure 0.23. Describe and explain the pattern of data shown on the graph as temperature increases. Describe and explain. So describe is writing down what you can see from the graph, and then explaining is why is this happening? So what is the science? An increase in pigment increases absorbance. At lower temperatures, there is no change in absorbance because the membrane is still intact. At higher temperatures, there is a steep increase in absorbance because the pigment leaks out when the membrane becomes more permeable due to the phospholipids moving further apart. The kidney is one of the organs of excretion in vertebrate animals. Figure 2.1 shows a light micrograph of a section through a kidney cortex. Name parts of the kidney labelled A and B. So the glomerulus is the network of blood capillaries that sits in the Bowman's capsule. A is the glomerulus and B is the Bowman's capsule. You would expect to see white space inside the Bowman's capsule because it is leading into duct space. Calculate the length of the line X to Y. Give your answer in micrometers to two significant figures. So use the I-am triangle, and I know that M for magnification is 160. I can get that off of the picture. I need to find out what A is. I need to find out the actual size. So I can measure my image size, which is on my picture 3 centimeters. When you're looking at mark schemes for these questions, be careful because your answer is probably not going to be the same as these ones because your printers print out at different sizes. So don't worry about it too much. Just concentrate on whether you got the method right. 3 centimeters, I know my answer has got to be in micrometers. So I have to convert 3 centimeters into micrometers. And the easiest thing I always do is I actually measure in millimeters, or you can convert your 3 centimeters into 30 millimeters, and then you know you've just got to times by 1,000. So it'll be 30,000 micrometers divided by 160 gives a 187.5. We need to pop that to two significant figures, so that would be 190. Studies of the cell surface membranes of the distal convoluted tubule have provided the following evidence. Sodium-potassium pumps move potassium ions from the blood to the tubule fluid, move sodium ions from the tubule fluid to the blood, use ATP in these processes. Sodium-calcium cotransport proteins move calcium ions from tubule fluid to the blood, move sodium ions into the tubule fluid, use the electrochemical gradient of sodium ions to drive this process. Using this information and your own knowledge, compare the processes occurring in the proximal and distal convoluted tubules. So by the word compare, you need to make sure you include similarities and differences in your answers. And this question depends on you being able to recall what you do know about the proximal convoluted tubule and then compare it to what's above. What you mustn't do is just simply write those sentences above on your lined bit of paper. So it's got to be a comparison. So your answers should be something like this. Both proximal and distal convoluted tubules use active transport and co-transport. They both involve selective reabsorption and the use of sodium ions. The distal convoluted tubule involves the use of calcium ions, but the proximal convoluted tubule does not. In the distal convoluted tubule, only ions are used in co-transport, but in the proximal convoluted tubule, amino acids and glucose are co-transported with sodium ions. Nephrogenic diabetes insipidus is a disease of the kidney that affects the regulation of water potential in the blood. One cause is lithium poisoning. Lithium ions enter the kidney tubules through sodium channels. This prevents the cells of the collecting duct from responding to ADH in the blood. State and explain one symptom you would expect to observe as a result of nephrogenic diabetes insipidus. Well, if we remember our structure of our nephron, ADH makes the collecting duct more permeable, so more water leaves the nephron and is reabsorbed into the blood. If the collecting duct is not responded to ADH, then less water will be reabsorbed into the blood. Then that will mean a greater volume of water in the urine. Now, the reason that will happen is because there will be fewer aquaporins which will fuse with the plasma membranes of the collecting duct cells, because of course ADH stimulates the vesicles in the collecting duct cells to fuse with the membrane, and those little vesicles got those aquaporins in. So all those keywords in there as well. You have stated a symptom and you have explained it using high level terminology. Figure 17.2 is an image of a Kupffer cell from the liver. The diameter of the Kupffer cell in the image is 9.1 centimeters. Now, I appreciate that is quite confusing because it isn't actually 9.1 centimeters on the screen or on your page or whatever, but it is telling you that the size of the image is 9.1 centimeters for the diameter. Okay, we'll go with that. Assuming it is spherical, calculate the actual volume of this cell. Give your answer to 4 significant figures and show your working. So you have a scale bar here, which is the actual size is 4 micrometers. Now, depending on your printer, whether you've reduced this, your answer may be different depending on how long your scale bar is. So you've just got to make sure you stick with the same method. And like I said before, don't worry too much if your answer is different to a mark scheme, because the exam question originally may have been at a slightly different size. So if we have a look here, this scale bar I'm measuring as 1 centimetre is 4 micrometers. So I set it out like this. And then I know that the diameter is 9.1 centimeters because they said it in the question. And that is 9.1 times greater than 1 centimeter. So what is 9.1 greater than 4 micrometers is 36.4 micrometers. So that is the diameter. The diameter is 9.1 centimeters of image size, which in actual terms is 36.4. But to find the volume of a sphere is 4/3 pi r cubed, r being the radius. So we're going to have to divide 36.4 by 2 to give us the radius, which is 18.2. And then we just pop that into the volume of a sphere equation, which gives us an answer of 25,252, but we've been asked to put that to 4 significant figures, so it's going to be 25250, and don't forget your units, which is going to be micrometers cubed. Which type of microscope has been used to obtain this image? Explain your answer. That is going to be a transmission electron microscope because organelles are visible and it has a high magnification and resolution. You won't get a mark if you put scanning electron microscope because it is not a 3D image. Last question. This is a diagram of the external view of a mammalian liver. We have got to identify with reasons each of the blood vessels labelled A to C. You cannot just write the name, you won't get the mark. So let's have a quick look. A is the hepatic vein. We know this because blood is leaving the liver. B is the hepatic artery. Blood is entering the liver. And C is the hepatic portal vein. It is a branched vessel and it brings blood from the intestines. So now all we need to do is just write that on the lines. And that is it. Thanks for watching. I hope you found it useful. If you did, don't forget to like and subscribe for more content.